In this part of the lecture, we shall study the effects of changes in the mechanical load that is connected to the shaft of the rotor of a synchronous motor. We have already studied the working of synchronous motors. When we supply three-phase currents to these three-phase coils placed on the stator of a synchronous motor, a uniform rotating magnetic field is generated. This rotating magnetic field, Bs, rotates with a synchronous speed. There is another magnetic field, Br, due to field windings on the rotor, and due to the interaction of the two magnetic fields, torque is induced. And this induced torque is such that it will tend to align both the magnetic fields. Since Bs is rotating with synchronous speed, therefore Br will chase this magnetic field. That is, rotor will also start rotating with the synchronous speed. The expression for induced torque for synchronous motor, we have already derived this expression. Induced torque is given by K Br cross B net, which can also be written in this form, where this delta is called torque angle. It is angle between Br and B net. Here is also the angle between V phase and EA, the internal generated voltage. That is, we have already sketched the phasor diagrams for synchronous motors. We had this situation. The phase voltage, phasor for internal generated voltage, and the angle between the two is the torque angle. And this phasor JIAXS, that is perpendicular to the phasor for current. So this delta is angle between the phasor for V phase and EA. And since this B net is responsible for production of V phase, therefore the phasor for B net is in phase with phasor for V phase. Phasor for B net in phase with phasor for V phi, and this Br is responsible for generation of EA. Therefore, this phasor is parallel to phasor for EA. We have this phasor. And the angle between the two is delta. What is phasor for Bs? For the case of synchronous motor, both B net and Br, they lag behind Bs. So phasor for Bs is over here, parallel to this phasor. So what will happen when the mechanical load connected to this synchronous motor is increased? So when mechanical load connected to shaft of the motor is increased, this rotor will tend to slow down. However, because Bs, that is rotating with uniform velocity, that is equal to omega sync, therefore this Br will lag further behind it. Br is due to this rotor, and since rotor has slowed down, so Br will further lag behind B net. That is, when load torque is increased, delta, the torque angle, will also increase, and an increase in the torque angle will then in turn result into increase in induced torque. Induced torque depends upon sine of delta. As delta is increased, sine of delta will increase, and hence induced torque will also increase. So what will happen due to increase in induced torque? This rotor will again gain the speed, and after the transients, the induced torque will become equal to the load torque, and then this rotor will again keep on rotating with synchronous speed, but now with an increased torque angle. So this rotor, when load is increased, after transients, this rotor will again start rotating with synchronous speed, but now with increased delta, increased torque angle. We can also explain all these points with the help of these phasor diagrams. So what we observe is that EA, the internal generated voltage, that is given by K phi into omega. And since a rotor always rotates with synchronous speed after transients have died out, so this omega is constant. And what about flux? That flux depends upon the field current, and changes in load that has no effect on changes in the field current, so flux is also constant. That means that EA, magnitude of EA, also remains constant. It is independent of the load. No matter how much load you have connected, the magnitude of internal generated voltage remains constant. And the torque angle increases. That is, we have for this phasor diagram, let me redraw it over here. The same phasor diagram sketched over here again. What will happen when you increase the load connected to the motor? The torque angle will increase. This length will remain the same. Magnitude of EA is same. That is, this vector, this phasor, will move downwards along this line. With the increased load, we have this situation. This is EA1 and this is EA2. The length of this vector is equal to the length of this vector, because magnitude of EA does not depend upon the load, mechanical load, which is connected to the rotor. And however, the torque angle that is increased as you increase the load. What happens to the armature current? So this phasor corresponding to new situation, we have this thing, and then perpendicular to it is the armature current. What we see is that length of this vector is larger than this length of this vector. Since XS is constant, it means that IA has been increased. So length IA2, this is vector IA2, which corresponds to increased load. So as you increase the mechanical load connected to the motor, the armature current increases and this torque angle also increases. This blue line, these blue phasors correspond to increased load. If you further increase the load, the torque angle further increases, length of this thing remains the same. So let's draw this situation over here. This thick line corresponds to EA3, that is further increase in the load torque, and then this is JIA3 XS, and here is this length is still larger than this one, and you have more increase in armature current. So this thick line corresponds to further increase in the load torque. That is, this vector for EA swings down along this curve. So this is phasor diagrams for the synchronous motor corresponding to different loads. This length from here to here, that is equal to EA sine delta. That is proportional to the power of this motor, because we know that we have derived the expression for power for synchronous motor that was given by 3 V phase sine delta over xs. So if this supplied voltage, that is constant, xs is constant, so the power of this motor that is proportional to sine of delta. Here EA is missing over here. EA into sine of delta. So this thing is proportional to power. Where is the output power of this motor? The output power that is equal to the load torque multiplied by speed of the rotation. So from here what we observe is that since this speed is constant, as we increase the load torque, the power increases. That is this length, the this component also increases, which is obvious from here. Corresponding to first case, we had this much output power, and then corresponding to increased load, this power, that is the vertical component of this vector that has increased, and corresponding to further increase in the load torque, we have this situation, further increase in the output power of the motor. So with this discussion, we can also talk about the torque speed characteristics of synchronous motor. So what we have observed is that if we change the load connected to the rotor, to the shaft of this synchronous motor, after transients, this rotor again gains the synchronous speed. That means that the speed of this rotor that is independent of the connected load, that always remains constant. Therefore, we have these torque speed characteristics for synchronous motor. Torque on this axis and speed on this axis. So no matter how much torque you have applied to the motor, it keeps on rotating always with synchronous speed. This is synchronous speed. Synchronous speed is determined by the frequency of the voltage signal that is supplied to armature windings and the number of poles that are there on the rotor. To how much extent we can increase the load torque? So we know that the induced torque, that is given by, we have derived this relation in one of previous lectures. So this is expression for induced torque, and the maximum torque that we can get out of this synchronous motor, induced torque maximum, that corresponds to delta equal to 90 degrees. That is the maximum torque that we can get out of this synchronous motor. And if applied torque, the load torque, is increased beyond this maximum torque, the motor will stop. Rather, there will be high vibrations in the this synchronous motor, and that will damage the motor. Why vibrations? We shall talk about this point in more details when we shall be talking about starting problems with synchronous motors. So this is the maximum torque, and if the load torque increases beyond this torque, the motor will just stop, rather will be damaged. Generally, the rated torque for a synchronous motor, that is much less than the maximum torque, usually 3 times less than the this maximum torque. So rated torque, which is also called full load torque, that is much smaller than the maximum torque. And therefore, up to the rated conditions, if load is increased, this rotor will always rotate with synchronous speed. So here from this expression we also observe that this phase voltage, that is the voltage connected to stator windings, and EA, what is EA? That is dependent upon the field current. EA is dependent upon the field current, the current supplied to windings on the rotor. Therefore, for a given motor, we can further increase the maximum torque that can be provided by the motor by increasing the field current, by increasing EA. So what will be the effects of increasing field current on the working of this synchronous motor? We shall talk about this in the next part of this lecture.